Hello everyone, this is Qiaojun from Extension Robotics Lab at UC San Diego. Today I'm presenting our work, Mesh Reconstruction from Aerial Images for Outdoor Terrain Mapping using joint 2D-3D learning. UAVs are widely used in our daily life. We can fly a UAV to build a 3D environment map. Sparse feature-based long VIO is fast, but can only provide a map of sparse 3D points. Dense depth prediction of 3D surface reconstruction is usually done offline. Our question is, can we directly leverage the sparse depth points to recover dense depth prediction as well as the 3D surface? Our main idea is to build a mesh. Mesh can represent a 3D surface and it can render a dense depth map. We are using the sparse depth measurements as well as the RGB image as the inputs. Motivated by the sparse depth completion problem, we tackle it following a two-step fashion: initialization and refinement. In the initialization stage, we only use the sparse depth measurements. We initialize a 3D triangle mesh with a regular grid pattern like a chessboard. We use a mesh differentiable renderer to calculate a 2D render loss and optimize the mesh vertices to get an initial mesh. Here's an overview of the mesh refinement stage. We first extract 2D features from the image inputs. Then we use vertex image alignment to retrieve mesh vertex features from the 2D feature maps. We then apply 3D graph convolution on the 3D mesh and derive the vertex offset to deform the mesh. The refined mesh is fed to calculate the error with regard to the ground truth and also fed back to the vertex image alignment again if there's one more refinement stage. The vertex image alignment associates the 2D features with the 3D mesh vertices. We project each mesh vertex onto the image frame UV coordinate and retrieve the 2D features at different layers. All the features are concatenated to form the vertex feature. Here we show some rendered depth maps from the predicted mesh. SD-try is a baseline method that triangulates the sparse depth points. Compared with the initialized mesh and the SD-try mesh, the refined mesh rendered depth is better recovered, especially at the building boundaries regions. Here are more qualitative results, and we also show the 3D mesh. The sharp vertical transition of the buildings are reconstructed accurately with just a limited number of mesh vertices, around 1,000. Compared with dense depth map that store every single pixel, the mesh representation is more efficient and it provides a complete 3D surface. We have proposed the mesh reconstruction for a single view. With multiple local mesh and known camera pose, we can convert all the local mesh to the global frame and build a large terrain map.